Swayam Prabha. Digital India. Educated India.
Hello everybody. Today I am giving the second lecture of the module 7. As you remember that module 7 was on the approximate method for solving the buckling of thin plates. Previously we have discussed the buckling of thin plates using the exact analysis, and two boundary conditions we have seen the general solution. One is your this Navier's boundary condition that all edges were simply supported, and in another cases two edges, opposite edges are simply supported, other two edges may have any other condition. So, based on that Navier and Levy's boundary conditions, we have obtained the critical stresses of the thin plate using exact analysis. Then I have discussed the approximate method for finding the buckling load of the thin plate, and in that respect first I discussed the Rayleigh's solution, and then I discussed the Galerkin method for finding the buckling load. So, today I will discuss another very useful method for finding the buckling load of plate using the finite difference scheme. So, as you know that plate buckling or even say plate bending and also the vibration problems of any physical model, say beam, arch, plate, string, then this can be solved by exact method, and sometimes the exact solution is not available. Then we take the help of approximate method. So, finite difference is one of the approximate method for solution of the physical problem like your bending, buckling and then vibration in our structural mechanics or solid mechanics. And the most important thing in finite difference method is the control of error. That can be done by suitably adjusting the mesh sizes in this finite difference method. So, the most essential requirement of the finite difference method is first to express the differential equation, that is the governing differential equation related to the problem in finite difference form. Then we use this finite difference form of the equation at the particular node of a structure that is that was divided by different grid lines, and then we get a n number of simultaneous equations, linear simultaneous algebraic equation, which required to be solved to find out the unknown deflection of the plate. Here problem we are discussing is related to the plate. So, we will be talking about the deflection of the plate, and this deflection is the only the unknown variables in the domain of the plate that we have to find out, and from this deflection the other quantities can be found out. But as you know that finite this plate buckling or any buckling problem is a homogeneous boundary value problem. So, for non-trivial solution we will get a this characteristic equation to find out the critical value of the load, or in discrete form we actually convert this to standard eigenvalue problem and then we solve for the eigenvalues. Okay. Now, let us see the differential equation. As you know that differential equation of the plate subjected to the axial compression Nx and Ny and the in plane shear Nxy is given by this equation, that is del 4 W plus Nx by d del square W by del x square plus Ny by d del square W by del y square plus 2 Nxy by d del square W by del x del y equal to 0. And there is no transverse load because the buckling is a homogeneous problem. So, we take this transverse load that is acting on the beam is to be 0 for finding the critical load. Just like your free vibration analysis, that we find out the natural frequency of the system, whether it is beam, plate or cable, then we put the external load to be 0 and we solve this homogeneous problem. So, similar is the situation in case of buckling. We take the transverse loading on the beam to be 0 and we find the eigenvalues or this characteristic values of this problem. Okay. So, now to apply this differential equation in finite difference scheme, we first require to obtain the derivatives appearing in this equation in difference form. So, first we have to obtain the first derivative in the difference form and then second derivative, third derivative up to fourth derivative, and then we also need the mixed derivative, that is involving the twist curvature in this case of membrane shear. Okay. So, let us see, say a domain of the plate, here it is shown and this is divided into several divisions, and for simplicity I am taking the equal size of the mesh in both direction x and y, but it may be different also. For example, here in this x direction I am taking h, y direction is also h, but it may be say in the x direction it may be h, in y direction it may be say h 1, but equal mesh size is suitable for a plate which is square in shape. In rectangular plate, of course, we can vary the mesh sizes. Okay. So, the plate is divided into number of divisions, small divisions, and you can see that say it is a node which reference to which we will discuss the difference form of the derivative. Okay. So, let us consider that 0 is a node and 1, 2, 3, 4, 5 etcetera the node number along the x direction, and in the positive direction of the x axis the positive sign, that is it is plus 1 plus 2 like that, and in the negative direction we have just indicated this by minus 1, minus 2, minus 3. But this is not mandatory, one can take any other convention to express the node also. So, node number should be first given and then we with reference to the nodes, particular node we will find the first derivative, second derivative, third derivative etcetera in difference form. Okay. So, now let us consider the deflection of point O, that is node O or 0 whatever you call, is W naught. Okay. And at points 1, 2, 3 the deflections are W 1, W 2, W 3. Okay. And in the backward direction, that is towards the negative x axis, it is minus 1, minus 2, minus 3. So, node numbers are given, and in the y direction, since downward direction is taken as the positive direction of the y axis. So, I am taking 1, 2, 3 etcetera is the node number in the downward direction of the y axis, and minus 1, minus 2, minus 3 in the upward direction, because here the downward direction is taken as the positive direction. Okay. So, if I consider the slope of the deflected surface along the x direction at node 0, so the slope you can see that the deflection magnitude is here W naught and here it is W 1. So, W naught to W 1 there is a variation of displacement and therefore, the slope exists, and similarly on the negative direction, that is W minus 1 is the deflection at node minus 1. So, there is also the slope, that is the variation of the displacement. Okay. So, now if I compute the slope between the node say W 1 and W naught, then slope will be W 1 minus W naught divided by h. So, I have calculated the slope taking the forward values of the deflection. Now, if I take the backward deflection value, then I will get the slope at W naught at node 0 or O as W naught minus W minus 1 divided by h. So, two slopes when added and taken average, then we get the slope at node 0. So, that means it represents del W by del x at node 0 or O represents the average slope between this 1 and minus 1. So, you can see here 1 by 2 h is coming, because the distance between this 1 and minus 1 is 2 h, and after simplification the expression becomes 1 by 2 h bracket W 1 minus W minus 1. So, this is the expression for slope, a basic expression for the derivative, first derivative of W in x direction. Similarly, the derivative in the y direction can be written. So, if I take the y direction, then here you can see that 0 1 minus 1, these are the nodes, and here similarly it can be written the del W by del x at node O is like that W 1 minus W minus 1 by 2 h, but this will be in the y direction. Okay. Y direction deflection curve is given here, shown here. Okay. Now, let us come to the second derivative. So, this is the slope which can be represented in molecular form, which is easy to remember and the convenient for use in actually the solving the problem. This form is very much suitable. So, if you see the del W by del x at node O, it can be written here like that. So, at node O we found the slope and it was given by W 1 minus W minus 1, but the value of deflection at node O is absent in this expression. So, therefore, if I see the coefficient of this deflected surface, then here for W 1 it is coefficient is 1, W minus 1 the coefficient is minus 1, because the negative sign is there, and for W naught the coefficient is 0, because no W naught appears. So, therefore, I can write in this molecular form like that 1 by 2 h is the distance between node 1 and minus 1, and this is given say right hand side this is W 1, the coefficient is plus 1, and towards the left hand side it is minus 1 W minus 1 and coefficient is minus 1, and central value, that is W naught, does not appear in the expression. So, this value is taken at 0. So, this form is suitable, because when we want to compute the slope at any point, just we place the stencil to the finite difference mesh centering this double circle point to the node where we want the slope. Okay. So, double circle point refers to the point under consideration. Okay. So, similarly, if we go to other point, say if I want to find the slope at 3, then I will write that W 4 minus W 2 divided by 2 h, because the mesh size is taken same, and here W 3 coefficient is 0. So, therefore, naturally there will be no value here. So, 0 will be appearing there also in the double circle, there is the center node. Okay. Now, if I calculate the second derivative of the expression, then rate of change of slope is to be evaluated. So, del by del x, del w by del x 0. So, this quantity we have already calculated. So, now this can be calculated as 1 by h, because we already calculated del w by del x, and we again take the rate of change of this quantity. So, therefore, w 1 minus w naught divided by h, and then again w naught minus w minus 1 h, because this is taken between points h by 2 and minus h by 2 for curvature. So, therefore, h by 2 to minus h by 2, the gap is h. So, therefore, h appears here, and if we consider the node 0, that is then towards the right hand side, the other deflected deflection value is w 1. So, w 1 minus 0 divided by h, and then change is towards the left, if you see w naught minus w minus 1 divided by h. After simplifying this expression, it can be written as w minus 1 minus 2 w naught plus w 1 divided by h square. So, you are getting the second derivative, that is the curvature of the deflected surface. Okay. So, this can be written in the molecular form or stencil form, and the stencil form will be, say again 3 point will be there, but here the coefficient will be h square, and there it is plus 1 and there it is plus 1, and here it will be minus 2. Although I have not represented here, but in the later expression you will find this curvature appearing in the molecular form. Okay. So, now the fourth derivative, that is the highest derivative in the plate equation, is to be evaluated. So, del 4 w del x to the power 4 at point node O, node O is this, we want to calculate the fourth derivative. Okay. Again the second derivative is differentiated 2 times to get the fourth derivative. Okay. So, this we have already calculated. So, we have written here in the molecular form that I have told you. Molecular form of this will be like that, 1 by h square minus 2, and minus 2 is the central point, and then 1, and towards the right it is also 1. So, this is this point, this operator, okay, this operator is this, and then again del square w del x square here, but here w value is taken here w 1, that is w minus 1, but coefficient is plus 1, then w 1 coefficient is plus 1, and this is w naught, that is coefficient is minus 2. Okay. So, term by term multiplication you can get the arrange it in this form. So, if you multiply it, say 1, then minus 2, then 1, we are doing this first row, then second row if you do the multiplication, minus 2, 2 minus 2 4, then minus 2 1 is minus 2, then the last quantity, that is 1. So, 1 into 1 1, then 1 minus 2 is minus 2, then 1 into 1 is 1. Then you add this, you will get the fourth derivative. So, after adding we get the first term is 1, second term is minus 4, third term is 6, then fourth term is minus 4 and 1. So, you can see here that this the fourth derivative in the molecular form is written, the central value is 6, coefficient of deflection in the nodal point, there is the node centering which you will write the finite difference equation, that coefficient is 6, and towards right and towards left the same coefficient appears, because it is even number of derivative. So, the quantities are symmetric. So, you are getting this minus 4 1 towards the right side, and towards the left side it is also minus 4 1. So, interestingly you will see that odd derivative are antisymmetric and even derivatives are symmetric. So, after getting the fourth derivative, now the pattern in the y direction can also be written just by rotating the derivative that is found with respect to x by 90 degrees. So, if I rotate this with 90 degree, then I can get del w by del y, just rotation by 90 degrees. Similarly, del square w by del y square, rotating this quantity is del square w by del x square. So, if I rotate this quantity, this becomes minus 2, in upward it is 1 and this is 1. Okay. So, horizontal direction is x direction and vertical direction is y direction. So, it is written like that. Okay. So, then Laplacian operator, that is del square w, we need sometimes, because this if under the biaxial compression and the biaxial compression, the equal amount of compression is applied in both x and y direction in the plate, then you will find that this Laplacian equation is necessary. So, let us also express this del square w by del x square plus del square w by del y square. So, we have found that second derivative of w with respect to x is 1 by h square 1 minus 2 1. So, that means minus 2 is the coefficient of the deflection value at the node where you want to place the stencil. Then towards right it is 1 and this is 1. Similarly, for second derivative in the y direction is vertical. So, we write in the vertical line and we are writing say minus 2 central value, coefficient of the central deflection, and then upward it is plus 1 and it is downward it is plus 1. Since the even derivatives are symmetric, so there is no change of sign to, if I consider the coefficient in the top and bottom. Similarly, if I consider the coefficient towards left and towards right, there is no change in the sign. So, after addition of this, you can see that Laplacian operator appears in this form 1 by h square 1, then minus 4 1, because minus 2 when added it becomes minus 4, then 1 in the top and bottom again 1 and this left and right also coefficient 1. So, this Laplacian operator is important when we consider the plate under biaxial compression of equal magnitude okay, in buckling problem. Okay. So, mixed derivative also required, because if I consider the membrane shear force or shear buckling of the plate, then we have to consider this term that is associated with the nxy term that I have shown in this slide, that nxy by d and del square w by del x del y. So, mixed derivative term is associated with nxy. So, we should also know this the finite difference form of the mixed derivative. Okay. So, let us see the mixed derivative now can be written as this 1 0, that is central value is 0 and towards right and towards this left it is also 0 coefficient, and you will get the corner values are towards the left hand side it is 1, top and bottom in the left hand side it is minus 1. In the right hand side you will find that in the top it is minus 1 and in the bottom it is 1, and you can see the pattern that it appears as a antisymmetric quantity. Okay. So, now so we have got this fourth derivative. So, now fourth derivative in x direction I have obtained, and as the y direction also can be written just by aligning the stencil in the vertical direction. So, after arranging this you will get the fourth derivative, that is the del 4 w, that is the biharmonic operator that is used with the deflection surface to form the plate equation. So, del 4 w is now is equal to del square w, that is del square w we have got that is the Laplacian operator we have got here. This is the Laplacian operator, okay, and the Laplacian operator is this, and when it operates with W, it is this. The W should be associated with this. So, therefore, we can write this as this del square W and del square. So, two operators, one is operator Laplacian operator and this is del square W that we have already obtained. So, now after expansion that can also be written as del to the power 4 W by del x to the power 4 plus 2 del to the power 4 W by del x square del y square plus del to the power 4 W by del y to the power 4. So, after collecting all the terms, now the appearance of this del 4 W is like that. You can see in the central line, horizontal line, the stencil has to cover the 5 points. Okay. If this is the central point, that is central point, I mean where you are centering the stencil. Suppose there are say 10, 12 nodes and at particular node say 5 you are centering the stencil, then this value has to be placed in the node 5 and then automatically other node other molecule will get their position. Okay. So, towards left you are finding that minus 8 1 in the central line and this is minus 8 towards the right also minus 8 1. It is symmetrical because it is the del 4 W is your this even derivative. So, therefore, in the vertical line also you are getting symmetric and there other lines are also have symmetrical distribution. So, 2 minus 8 2 and here also you are seeing 2 minus 8 2 and so 5 points need to be covered by this stencil in the central position as well as vertical central horizontal position as well as central vertical position. Central position I mean that where you center the stencil. Centering may be done at the center node or it may be at any other node, it does not matter. So, we should also, though the bending moment expressions are not required, but to apply the boundary conditions in finite difference method, we require to know the bending moment expression in finite difference form, okay, and shear force expression also. So, bending moment expression is nothing but combination of this del square W by del x square plus mu is the Poisson ratio del square W by del y square. Okay. And if you combine these two derivative, okay, and del square W by del y square is multiplied by mu, that is Poisson ratio, we can write it 1 minus 2 1 and this is plus mu minus 2 1 and 1. So, after adding this you will get the central node is here minus 2 into mu and in the upward direction you are finding then mu into 1 it is there, in the downward also downward node it is also mu into 1 and other nodes are 1 and 1. So, this is the full tensile for m x. Similarly, we can write the bending moment m y. So, m y is written like that, you can see the difference this is just placed now in the horizontal position, this vertical low is now placed in the horizontal position. So, we get this the m y. Okay. So, m y is obtained like that. Then m x y, the mixed derivative is also needed, because if we consider the shear buckling, how the shear buckling equation is formed? Shear buckling equation is formed with the term 2 n x y del square w del x del y and other in plane forces, that is n x and n y, are associated with the second derivative of their respective directions. Okay. So, therefore, this m x y has to be known also for this shear problems, especially shear buckling problem. I mean that mixed derivative should be known for shear buckling problem, and also the m x y and the shear force the Qx or Qy has to be combined to give a Kirchhoff's S shear. That is very important for free edge condition, because free edge condition, you know that there are three conditions that have to be equated to 0. What are these three conditions? One condition is that bending moment is 0, second condition is this twisting moment, that is mxy or myx is 0, and third condition is qx or qy, whatever may be as per their h location, is to be 0. So, the three three quantities to be equated to 0. Later on that Kirchhoff have modified this condition and have given two expression instead of that. So, that is mxy is combined with shear force qx or qy to give the S shear, one S shear, that is Vx or Vy. So, therefore, the mxy expression is also needed for calculating the S shear value. Okay. So, qx, that is the shear force in the plate along the edge where the x coordinate is specified and y is varying, then it is given like that minus d del by del x del square w. Del square w we have already evaluated, now we operate with this. Del by del x operator is already known, that is it is 1 by 2 h minus 1 0 plus 1. So, and this operator is also known. So, when we operate this del by del x with this Laplacian operator del square w, Laplacian equation del square w, then we get this stencil for qx. So, qx is now minus d by 2 h cube, and in the horizontal line centrally you are getting minus 1 4 0 minus 4 1 minus 1 plus 4 0 minus 4 1, and you can note here that the values are antisymmetric. So, towards the right it is minus 4, but towards the left in the corresponding location it is plus 4. Similarly, in other also minus 1 and plus 1. So, in the vertical direction also you can note this, and in the central location in the vertical direction this is 0. Okay. So, you are getting qx. So, therefore, Vx, that is along the x, say x is equal to a or some edge at the boundary, you want to apply the S shear condition as a boundary condition. Another boundary condition at the edge is say bending moment, especially for free edge. The boundary condition becomes, if x is equal to a edge is free, then bending moment condition at x is equal to, the boundary condition at x is equal to a will be mx equal to 0 and Vx equal to 0. So, instead of three equation that we earlier told, that mx equal to 0, qx equal to 0 and Vx and mxy equal to 0, we write now two condition, that is the qx and mxy are combined. So, after combining these two terms, we get the S shear force Vx. So, S shear force is also containing the third derivatives, the odd number of odd derivatives, and then you get that this is also appearing antisymmetrically. So, antisymmetric functions, antisymmetric values are noted in the quantity Vx. So, if we want this Vy, then just rotating the pattern by 90 degree, the finite difference for Vx, Qx, Vx etcetera can be found, but mxy is equal to myx. So, the expression for mxy will remain valid for myx also. Okay. Now, boundary condition that we encounter in the plate buckling problem, this may be simply supported edge or fixed edge or may be free edge. Okay. Now, free edge condition I have not mentioned here, because the free edge condition is slightly lengthy, but one can apply the free edge condition using this Vx at the free edge and Qx and mx or my at the free edge to be 0. Okay. Now, when we apply, suppose you apply this condition, say m x is this 1 minus 2 minus 2 mu minus 1. So, if this m x is to be applied at the boundary, that boundary value, if the node is falling in the boundary here, but you can see that one point is outside the boundary. So, that problem is overcome by taking a dummy point here, okay, and relating the displacement of the dummy point with the displacement of the real point, just image point, real image point. Okay. So, you can see here that if I consider a simply supported condition, just let me discuss with a figure. We consider a simply supported edge. Okay. This edge is simply supported. Okay. So, this is the plate domain that is shown by solid lines, but dotted lines are not really existing. It is thus taken for this finding the expression in terms of the displacement of the plate domain. Okay. Now, let us say at this edge m x equal to 0. So, our stencil was this for this bending moment. So, if I put this is the node. So, if I put this here, just I take this here, then at the boundary displacements are 0. So, you are getting the displacement of 2, displacement of 4 are 0, and displacement of this node say 0 is also 0, because this is falling on the boundary, but displacement of 3 is somewhat say W 3, and here we are getting some say imaginary node. Okay. So, that is the deflection is W 1, okay, but coefficient is plus 1 and plus 1. So, that means, if I now write this equation, then I have to write W 1 plus W 3 equal to 0, because this quantity if I write, this will be 0, because these nodes are, these molecules are falling on the boundaries. So, therefore, we can write W 1 plus W 3 equal to 0. That means, the W 1 that is falling outside the plate boundary, that is now expressed in terms of the displacement of the image point. Image point is 3, which is real point in the plate domain, and therefore, W 1 equal to minus W 3. So, in this way simply supported boundary condition is expressed. Okay. So, you can see this W 1 plus W 3 equal to 0. So, W 1 will be minus of W 3. So, deflected shape for purpose of expressing the value of the deflection value of the imaginary point in terms of deflection value of the real point is taken like that. Okay. Now, displacement of imaginary point, that we call the imaginary point W 1 is now equal to the negative of the displacement of the image point. So, now we come at the fixed edge condition. Okay. In the fixed edge condition, the two conditions are generally have to be satisfied. One is deflection is 0, another is slope along the normal to the edges should be 0. So, if it is the edge is x is equal to, suppose x is equal to a, this edge is fixed, then W is 0 at this edge, and also del W by del x equal to 0. Okay. Now, here the del W by del x 0, that means, if I write this in the stencil form, I can express this minus 1 0 minus 1 and it is W, that stencil we have already got it earlier. So, now this stencil is now put here. 0 is the node where we want to apply the boundary conditions. So, this fixed that is the slope, this stencil is first derivative stencil is put here at 0, and then we get that 2 points, this point is on the node on the boundary, this point is on the boundary. So, therefore, automatically it vanished, because the deflection at the boundary is 0, but this node is outside the boundary and with coefficient minus 1. So, say suppose this is the deflection W 1 and this is the deflection W 3. So, when we expand this stencil, we have to write now minus W 1 plus W 3, because the coefficient is minus 1. So, we have written minus 1 plus W 3 equal to 0. Therefore, W 1 equal to W 3. So, in this case the displacement of the imaginary point, this is the imaginary point, this point 1 is equal to the displacement of image point. So, that conclusion we have got after applying the boundary condition. Okay. So, we have applied the boundary condition at the edges with the simply supported condition, that is the bending moment is 0, and also the slope 0 at the fixed edge condition. So, two equations we have got, W 1 equal to W 3 for the fixed edge condition, where W 1 is the imaginary point deflection and W 3 is the corresponding image point. So, whenever it appears the imaginary point, we can now replace it by the displacement of the image point. So, similar was the case in case of simply supported edges, but you can see the difference here. Here the W 1 equal to W 3, but there you will get W 1 equal to minus W 3. There means in simply supported case you are getting W 1 equal to minus W 3, but in fixed edge condition you are getting W 1 equal to W 3. At the free edge, of course, the boundary conditions are bending moment equal to 0 and S shear force equal to 0. Now, let us consider a buckling of square plate simply supported along the edges under biaxial compression. So, we take a square plate just to illustrate the application of this method. The compression is along the x direction and along the y direction, both are same amount, and there is no membrane shear, there is no shear load. Okay. So, shear buckling is not considered here. So, therefore, the differential equation for buckling is now del 4 W plus n by d bracket del square W del x square plus del square W by del y square equal to 0. Because the n and ny is equal here. So, I have taken this the n common from both the curvature term del square W del x square and del square W del x square. So, the equation now in this form, the differential equation is now can be seen that it is like that del 4 W plus n by d bracket del square W del x square plus del square W by del y square equal to 0, where the meaning of d is the flexural rigidity of the plate and n is the axial compression and equal in both the direction. Okay. Let us solve this problem by finite difference form. Okay. Now, first we approximate, the approximation is that n is equal to 2, that means the plate is divided into two equal divisions along x and along y direction. So, a square plate whose side was a now divided into two divisions, a by 2 and a by 2. Okay. So, there are 4 divisions and this node here, because the other node if you consider all are falling in the boundary. So, therefore, deflection value will be 0, but central node, let us see, this deflection is W 1, that is only one node has to be considered here, and you can see that the other node, because if you see the molecular form of the finite difference equation of the plate, you can see that 5 nodes have to be covered in the horizontal direction centrally and vertical direction centrally also 5 nodes. So, therefore, other 2 nodes are falling outside the boundary and we have given it is W 1 W 1, but coefficient minus 1 I have given, because I have shown you that for simply supported case, if the deflection of the imaginary point is W 1 and corresponding image point is W 3, then W 1 equal to minus W 3. So, here the image point of this node is this central node W 1. So, for example, 1 node number is 1. So, therefore, the deflection here will be minus W 1 if the deflection here is W 1. Similarly, in other direction vertical direction, here deflection is minus W 1 and here it is minus W 1 and towards the right it is also minus W 1. Okay. So, this is the stencil of the buckling equation, and because this the del square W del x square plus del square W by del y square, these two terms are there. So, we have written these two quantities in finite difference form 1 minus 4 1 1 and 1. Okay. So, now placing this finite difference term, this is for plate bending and this is coming for this axial compression terms. Okay. So, then if you place this stencil here, this node 20 should be placed here, this double circle should be placed here. So, if you place double circle here, this minus 8 the coefficient here will go here, and naturally there is this node is falling on the boundary and therefore, deflection is 0. Okay. So, similarly, towards the left hand side it is also on the boundary, right hand side top it is also on the boundary, and here on the bottom it is also on the boundary. Similarly, this coefficient, that is this node, this circle that you are seeing, that 2 2 2 2, that are also falling on the corners, and this is because of simply supported edge, this plate is simply supported edge. So, deflection value at all points along the boundary is 0. So, that we are getting only say 20 W 1 by applying this equation. No other quantity can appear here. Then let us see this term n a square by d 1 minus minus 4 1 1 1 1 1 is vertically and 1 minus 4 1 is horizontally. That means, minus 4 coefficient is to be placed, circle with minus 4 coefficient has to be placed at the nodes. So, if I place this circle, that minus 4 containing the coefficient minus 4 here, other point say 1 is falling on the boundary, this is falling on the boundary, this is falling on the boundary, and this is also falling on the boundary. So, naturally the deflection is 0. So, hence finite difference equation now can be written 16 minus this 6, how 16 is coming, 20 minus 4, because 20 is there at the center and no other values are important there, because it is they are falling on the boundary, and this minus 4, because this is also again this minus 4. So, n a square by d minus 4 n a square by d, a square is coming because h is equal to a by 2. So, when you write n a square by d minus 4 into n a square by d and then put h is equal to a by 4, then this quantity will be minus n a square by d. Okay. So, for non trivial solution, this quantity inside the bracket should be 0. So, the critical load for this plate is now is 16 d by a square. So, by first approximation, that is by dividing the plate into two divisions, we now get this value, that critical load of the plate is given by 16 d by a square. So, let us see whether we can improve the accuracy of this method by increasing the number of divisions. Okay. So, in the next step we take the second approximation, we take number of division as 3. So, we divided the plate into 3 equal divisions. So, each division is now a by 3 by a by 3. So, side of a small square is now a by 3 by a by 3, that is the square, small square, and full plate was of the size A by A. So, 9 divisions are there in this plate total. So, now 9 equal squares are there. So, we now number the node. Now, because of symmetry, the deflection here say is the same deflection as that deflection. So, therefore, W 1 equal to W 1 and W 1 equal to W 1 because of symmetry. So, this value we have assigned now, okay. And this is boundary value wherever this plate stencils, the circles of the plate stencils fall on the boundary, then the deflection value is 0. And when we consider the boundary condition, that is bending moment is 0 at the simply supported edge, we encounter one imaginary node. So, that imaginary node for simply supported condition has a coefficient -1, and therefore, deflection value of the imaginary point that have to be taken to replace this is -W1 as compared to its deflection of the imaginary point. So, similarly, -W1 is written here, and here also -W1, here it is -W1, all are written accordingly. Okay. So, now place the stencil. Okay. So, this is the stencil for the buckling equation of the plate, that is you can tell it the molecular form. So, if we now place the stencil here, there are two parts, one is for plate bending that you can see del 4 W, and this is for buckling part, that is N square by D. So, now let us first place this. Okay. If I place this here, then 20 W 1. So, 20 W 1 is coming. Okay. Then here this circle is falling here. So, -8. Okay. Then this circle is falling here. So, -8. Okay. This one is falling on the boundary. So, 0 2 0 value. Okay. The circle 1 that is falling on the boundary. So, therefore, its value will not be considered because the boundary deflection is 0. Okay. Then on the other hand, this value, this circle 2 is falling here. So, this value is taken 2. Okay. Now, with red color 2 numbers are written -1 -1, that is just to indicate this are the node that are outside the plate domain, but the deflection of that imaginary point is now written in terms of deflection of the actual point, image point, by using the boundary condition, that is the bending moment condition to be 0 at the simply supported edges. So, therefore, one imaginary point we get here. If I place this stencil here, then this -W1 will be here corresponding to this W1. Then another imaginary point we get here. So, -W1. So, -1 is there. So, therefore, I have indicated in the red color this two imaginary point deflection, that is expressed in terms of the deflection of the corresponding point by using the bending moment 0 condition at the simply supported edges. So, this is for plate and plate bending, and for buckling the axial compression part. Now, if you place this stencil here, you can see the coefficient is -4. So, -4 W1 plus W1 plus W1 is there. Okay. Then plus W1 is there. Other nodes, say these nodes and these nodes are falling in the boundaries. So, therefore, they do not appear here. So, the equation for this N square by D, that is the buckling part, is written like that. So, after simplification, now we can write this, and putting 20 -8 plus 2 -1 and this is if you simplify it, it will be -2 W1. So, therefore, it is minus 2 W 1 N A square by D. By putting H is equal to A by 3, because we have divided the plate into 3 equal parts, we now write W 1 into 4 minus 2 N A square by 9 D equal to 0. So, therefore, the critical load for buckling now becomes 18 D by A square. So, let us compare the results that is obtained by finite difference method with the exact results. Now, exact result for this problem is available. So, if I see the differential equation is this and the S condition is simply supported, then I can take the double trigonometrical series, that Navier series, to find the solution of the deflection. That is, I want to solve it by exact method. So, therefore, substituting this in the differential equation, we now get this form, that is the double summation a m n m to the power 4 pi to the power 4 by a to the power 4 plus 2 m square n square pi square divided pi to the power 4 divided by a to the power 4 plus n to the power 4 pi to the power 4 divided by a to the power 4 minus n by d m square pi square by a square plus n square pi square by a square, then sin m pi x by a sin n pi y by a equal to 0. Okay. So, I can simplify this expression as like that, a m n equal to pi to the power 4 m square by a square plus n square by a square, because it is a square plate. So, minus n by d m square by m square pi square by a square plus n square pi square by a square, because a square plate is taken. So, that a is equal to b in this plate, and therefore, the double summation now appears as a m n sin m pi x by a sin n pi y by a, but a m and n are two different wave numbers that represents the wave number in the half wave number in the x direction, m represents the half wave number in x direction, n represents the half wave number in n direction. Okay. So, this equation is now written in this form, and for non-trivial solution one can see that n by d m square pi square by a square plus n square pi square by a square equal to pi to the power 4 m square by a square plus n square by a square whole square. Now, since it is a square plate, and after simplification we get the critical load is n is equal to pi square m square plus n square by a square by d, and the lowest value of load can be obtained, and this is easily observed that if m is equal to 1 and n is equal to 1, that means the plate buckles with half wave number in both x and y direction, then the lowest value of buckling load is obtained, and that will be the critical load. So, by putting m is equal to 1, n is equal to 1, we get the critical load for buckling as this. So, its value is 19.739 by a square d. So, this is the exact value. So, now in this table I compared the finite difference result with the exact results. So, we get this, the number of divisions, if it is 3 in the plate, then finite difference result gives 16 d by a square. Exact result is 19.739 d by a square. So, percentage difference of result or percentage error you can call is 18.9. So, when we say increase the division by 3, the critical load is 18 d by a square, but the exact value of the critical load is 19.739 d by a square, and here percentage difference is 8.8. So, that means by increasing the number of division, the accuracy is improved. Okay. Now, here again I give you one problem that you can see it is solved in a similar way, but the S condition is now altered. So, S condition is now clamped instead of simply supported, and this is the stencil for the plate buckling equation, and we take the this stencil, and because of symmetry you can see if this is the central deflection W 1, then because of symmetry this deflection is say this value of the deflection at this node is W2, here also W2, 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 and then also it is W3, W3, W3 and W3. Okay. And because of the fixed boundary condition, the deflection of the imaginary point here will be equal to the corresponding deflection of the image point. So, if this is the deflection of the image point W3, then this deflection will also be W3. So, similarly other deflection values are written. So, applying the plate equation, that is the buckling equation in point 1, okay, we get now say this stencil if I place here. So, 20 is there and here minus 8. So, minus 8 W2 and there again minus 8 is here, here minus 8 is there, here minus 8 is there. So, 4 minus 8. So, 4 into minus 8 W2, then this other value that here this 3 this point nodes are there W3, 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 W3. So, 4 and coefficient of this node is 2. So, therefore, 4 into 2 W3 we have written for plate, and other nodes, these nodes with coefficient 1, 1, 1, 1 is falling on the boundary, so they are not appearing here. And the buckling part now can be written, say this is value. So, this minus 4 into W1 plus this other say 1, this is all are same value. So, W2. So, it is written 4 into 1 into W2. So, this equation are now obtained like that. So, this is say equation 1. So, now at the point 2, if it is applied, then question of one imaginary point comes, because if you place the stencil here, then one point that is minus 8 is in the boundary, but this node will come here. So, one imaginary point is there. So, this value has to be expressed in terms of the corresponding image point value, and corresponding image point is 2, and this is for fixed condition, it is the deflection of the imaginary point is equal to the deflection of the image point. So, this term is coming here with W2 that I have indicated with the red color, okay, to understand that is due to the imaginary nodal deflection expressed in terms of corresponding image node deflection in the plate, inside the plate. So, plate equation is now written like that: 20 W2 minus 8 W3 minus 8 W3 minus 8 W1 plus 2 W2 plus 2 W2 plus 2 W2, and this W2 is coming due to imaginary point. And now, the buckling part is written, because this node is now placed here, this node is placed here. So, minus 4 W2 minus 4 W2, and there you are getting the other points, say this is W3 and this is W3. So, 2 W3 and this is W1. So, W1, and this value is falling here. So, naturally it will not come. So, therefore, we write this equation as this after simplification: minus 8 W1 plus 26 W2 minus 16 W3 plus n square by d W1 minus 4 W2 plus 2 W3 equal to 0. Okay. The plate equation in 3, node 3, let us come to the node 3. Okay. If you place the stencil in the node 3, first let me see that you will encounter one imaginary node here and another imaginary node at the bottom, one imaginary node towards left and another imaginary nodes at the bottom. So, therefore, two imaginary nodal deflection has to be now expressed in terms of corresponding image point. So, therefore, corresponding image points are 3. So, W3, W3 I have written, and other points are written as usual. So, W20, W3, minus 8 W2 minus 8 W2 plus 2 W1 plus W3 and plus W3. So, these are due to points which are lying outside the boundary, and this is expressed in terms of reflection of the points inside the boundary, the corresponding image point. Okay. So, writing this for the plate, and then we come for this buckling part, that is in plane force part. So, in plane forces the stencil is this n square by d 1 minus 4 1, and vertically it is 1 and 1. So, if I place here this node, then you can see minus 4 W 3, that is okay, and this node is coming here. So, this node is coming here and another node is coming here. So, 2 into W 2, and other two nodes, say 1 and this one, is falling on the boundary. So, naturally these values are 0. So, after simplification we get this equation. So, 3 equations now we have got, and these 3 equation now can be expressed in the matrix form, say A matrix, W matrix. Beta is a factor which is containing the buckling load n, and it is written as n square by d, and beta B W, where A is the coefficient matrix, that is 20 minus 32 8, the coefficients of W 1, W 2, W 3 etcetera in each equation. So, after writing this, the B equations are written as the coefficient of W 1, W 2, W 3 obtained from the in plane force part, okay, and that is obtained for plate bending part. So, this coefficient you can see minus 4, then 4, okay, like that it is written, all right. So, after obtaining, because these quantities are transferred in the right hand side. So, this sign will be reversed. Okay. So, therefore, it is 4 and this is minus 4, and this is 1. So, this is minus 1, this is minus 4, this is plus 4, and this is plus 2, this is minus 2, like that. And here no W 1 is appearing. So, W 1 coefficient is 0, and then 2, if it transferred to the right hand side, then minus 2, and this is transferred, when transferred to the right hand side, it will become plus 4, and W vector is composed of W 1, W 2, W 3. So, you can see, if I multiply this equation by B inverse, we can find an equation like that. If I multiply this equation by B inverse, then we can find this equation as a standard eigenvalue equation. So, here the eigenvalues of the D are obtained, because B inverse B is unit matrix or identity matrix, and B inverse A, that is a matrix D. So, eigenvalues of D are calculated, and it is found as 2.6464 and 4.7036 and 7.1500. And lowest eigenvalue will give this critical value of the buckling load. So, beta, taking beta is equal to 2.6464, we can now calculate the critical value of n as 2.6464 d by h square. Okay. And putting h is equal to a by 4, because a is the plate dimension and h is the mesh size. So, we now replace the mesh size with the plate dimension. We now get this 42.34 d by s square as the critical load. This can also be written as 4.29 d pi square by s square. Okay. So, let us summarize what we have done in today's lecture. In this lecture, finite difference method for buckling analysis of the thin plate is discussed. The governing differential equation for buckling is expressed in finite difference form first, and then we use this finite difference equation in solving two problems. One problem is simply supported square plate under biaxial compression, and second problem is clamped square plate, the plate which is also square, but the edges are clamped and also under equal biaxial compression. improvement of accuracy by increasing the number of mesh size was shown after comparing with the analytical results. Okay, thank you very much.